I'm Dan Mortensen. I'm the current chair of the Pacific Northwest section of the AES, and I'm really happy that you can join us and share this little respite from the affairs of the world. Now, as Rod said, he produced this meeting, Rod Evenson, and I'd like to introduce him as a committee member, and he will introduce Brian for us. Thank you.
Well, I'm Rod Evenson. I'm the local committee member for the AES and worked to get Brian into this to put on the presentation. This is Brian with Audio Precision, and he came up with a presentation for us. I'm hearing an echo of myself in the background.
Yeah, Brian, mute your phone.
Yep. Maybe I'm too close. But anyway, that's the way we went. I have a mysterious question too. Has anyone in the room ever done an alignment on a multi-track audio tape recorder? No? Yeah, one person. Okay. I had a very quick short story about that because I've done that myself. And if you know the procedure, you've got an alignment tape and it announces a test tone, and then it plays the test tone, and another test tone, and plays the test tone again. Anyway, I was doing this while babysitting a 4-year-old nephew, and he starts off on this story about this evil professor doctor, and he has a mummy laying on the table in front of him, and he has this big needle, and he sticks the mummy in the foot, and the mummy goes, ow. He sticks him in the ankle, and the mummy goes, ow. He sticks him in the arm, and the mummy goes, ow. He sticks him in the side, the mummy goes, ow. He sticks him in the face, the mummy goes, ow. And he goes to the other side, and so on through the appendages. And finally, the evil professor doctor, seeing that whatever he's doing is apparently bringing this long dead Egyptian mummy back to life, he says, good, everything hurts. And the alignment tape announces 16 kilohertz. Good. With that.
Just make sure you're live. Okay, thank you all for coming. Those of you here in Beaverton and those you on the Zoom call. So my name is Brian MacMillan. I'm a product owner, product manager here at Audio Precision. In previous lives, I worked at Detroit Automotive. I've been to Whidbey Island near Port Townsend as a folk dancer. I've been to the Wood Boat Festival. Worked in Stevenage in the UK. So I'll try to touch points with that. So do have the agenda up here. Certainly we only ask that you mute when you open your bottle of beer so the rest of us don't have to be tempted by that. So certainly feel free to ask questions during the presentation. There's nothing quite as bad as talking to a dead room. We all know that from audio. So it makes it more interesting for the presenter as well. So this year, AP is celebrating its 40th anniversary of shipping its first analyzer. So that's something we're very proud of. It definitely has a wealth of knowledge available. So we'll be sending out links to various app notes and videos. One of the things that we have is the audio measurement handbook available as PDF. So that's a very useful reference. And I kind of prefer it as a PDF because that way it takes up less space on my bookshelf. We'll be talking about levels. Go a little bit, I realize some of it may be a little bit starting at the, but I think it's interesting to revisit those, talk about gain, bandpass. I was originally trained in vibration, modal analysis. So I'll talk a little bit about FFT analysis and some of the pitfalls and challenges inherent to that. Talk a little bit about crosstalk both driven and undriven, a practical demonstration. Go into a little bit more detail on total harmonic distortion and noise and some of the related total harmonic distortion, because we'll get to those in the frequency. Also, we'll spend quite a bit of time on signal to noise ratio. It's one of those things like damping that it's so fundamental within the audio industry that they've come up with different ways of measuring it and describing it. So kind of give you a little bit of relationship, how those are related and how they're similar and how they're different. We'll talk about phase, that as we get more and more channels in the audio stream, phase becomes more and more important, and we'll go through some applications of that. And then we'll spend quite a long time because a lot of audio parameters are a function of frequency in terms of different ways of measuring the frequency response of a device. So we'll go back to the beginning with a step frequency through an acoustic response where you can measure without an anechoic chamber within a certain frequency range, up to some techniques that are open loop, allow you to use a transfer function for that. So I hope it's interesting to you. It was interesting in me in preparing it. So those of us, let me see if I can hide that. Oh, well, we won't worry. There we go. So we all work in audio. We all realize it is a big beast, and we don't, trying to characterize an audio system or human perception of sound is a bit like the blind man with the elephant. We all sense and perceive something differently. It's all part of the greater whole, but sometimes it doesn't really, you don't really realize that. So this is a classic, that I fall back on, and sometimes, I realize that I'm only perceiving part of the larger whole for it. And each one of these measurements is in itself, distortion, frequency response, they're all part of the same thing. Let's see. So I will be using our APX 500 software, but this is common to all audio analyzers. There's nothing specific, possibly when we get into the frequency response. So first thing that we'll recognize is that these are voltmeters. So the natural unit for measuring is inherently volts. Sometimes we can apply some additional information and measure amperage or power, but inherently they are a voltmeter. So volt is the natural unit. Next unit would be dB volt. That is where we have a reference of 1 volt. So if I turn on my generator here, I get 0 dB. If I knock it down by a decade, go down by 20 and 40. Are we ready for another corny joke, or we had our fill? I'm letting you decide here in the room, those that are out there. By all means. Thank you. Okay, so I won't take it too long, but basically Noah loads everybody up onto the ark. And, the waters recede, everybody piles out, and everything's going well. The elephants are reproducing, the chickens are reproducing. Unfortunately, the snakes are having a bit of a tough time. So, Noah doesn't want an angry God. So he goes and prays to God and says, hey, snakes aren't my favorite creature, but, I realize this is part of your plan. What can we do for the snakes? God tells him, go out into the woods. I'm not sure how the woods have survived through the floods, but it's immaterial to the joke. Chop down a tree and create an altar to me. So Noah does as instructed, saws down the tree, cuts it up into chunks, lashes it all together, stands back and says, okay, God, I've made an altar here for you. And God says to him, well, I've had you construct a log table so the adders can multiply. There's not many people who get that. Yeah, that's another groaner. I did you warn you of that, and that was my good coworker Marty Alexander, who yeah, probably a few more decades ago than I would like to admit. First told me that, but I'm trying my best to propagate it through there. So now we do have the benefit of our those who've gone before us have passed on the information. Some of that information is useful and some of it we need to reconsider. One of those I would posit would be the unit dBm. Has anybody seen dBm in their travels in the audio? Yeah, and you realize what the limitation of dBm, what assumption it makes. Yeah, dBm assumes that you're looking into 600 ohm. So it's not really a proper unit of measuring voltages in these modern day. So a dBu is a more modern unit, and that, if you are looking at 600 ohms, gives you the same answer as dBm. So again, there's things out there that we benefit from those before us, and then there's things out there that we don't aren't so useful. Another one that is common is gain. So that's where we take a look at the output of an amplifier. We know what the input was. So we take two voltage measurements to determine the gain. A lot of audio engineering measurement is measuring signal, but then noise, and then somewhere in between that. So we switch over to a sweep mode. We'll clear off the measurements. So here I'm doing a level sweep. So you can see up here at the top, I'm basically feeding in a signal, and then I'm measuring what I get out. You'll see that I hit a plateau here, where essentially I'm hitting the noise floor of my system. Now that's because I'm measuring a broadband RMS signal. I'm measuring from not quite zero, but close to zero, all the way out in frequency. So one technique that we have in order to get a little bit better signal is to apply some filtering to that. So now I'm going to, instead of looking from 0 to 20 kilohertz, I'm looking in an octave band around 1 kilohertz. So you'll see that as I get close to the noise floor, it was about 100 microvolts. Levels out. The T is indicating that the averaging technique is looking for a stable value, and it's letting me know that I've timed out on that stable value. So we are getting close to the noise floor, but we are able to perceive it further down. Now I can get a little bit more selective in having a narrow band select. So I can go from an octave to 1/24. And you'll see that it's a little bit more selective, so it actually goes a little bit lower because it's not getting the noise, all the way from 0 to 20 kilohertz. It's a very selective bandwidth. And for a long time, bandpass filters was a way to get a lower noise floor, but there are easier ways. Essentially, an FFT analyzer is a series of bandpass filters. So here we're raising up through levels. I think one of you was worked in heat transfer, if you recall. Fourier, the French mathematician, he was in Napoleon's time, and he was trying to solve a heat transfer equation because he was working on cannon. And key figure of merit of a cannon is how quickly you can reload it and fire again. And that's related to how quickly you can dissipate the heat in the barrel. So Napoleonic defense spending applied today for it. But it's a very powerful technique. It's enabled a lot of our digital life with the phones and things like that. So a lot of modern audio measurements are based on the FFT for it. One of the challenges, just like any filter, is it has a certain bandpass to it. So if we take a look, I'll knock down the resolution of this a little bit. Yeah, so it gets a little bit broader. Yeah, turn off the Now, this is right at the frequency of the FFT is analyzing at the frequency of the generator. If I move slightly to the side, so right now, let me turn on my cursor. Or just to pick up the signal here. The worst condition is exactly halfway between the two lines. So that would be 103. So we just need to be cognizant of where we are in the FFT. This used to be a problem when we had 6,400 lines of FFT analysis. Computational power has allowed us to have 1 million points of FFT. So this is not so critical anymore. In my past life, working in the automotive industry where we do run up and run down analysis, there you don't have infinite amount of time in order to measure it. There you had to play some games in terms of resolution versus the RPM change across the FFT block. In the audio world, we're a little bit blessed that we can run steady state for a decent amount of time. Some of our practitioners work in production test. They need to be cognizant of how long a measurement is. So sometimes they will have to optimize in terms of that measurement. So this is the signal portion, and that's fairly easy to measure. Again, being careful where we are in terms of the resolution to the signal. So there's the data here. The other thing we need to be aware of is the noise. So I'm going to run it at a couple different resolutions. You can also see that as I kick up the resolution, it gets much more selective. But the thing that I really want you to notice is that if I add more resolution, it appears the noise portion is falling. But does anybody want to conjecture that it is actually falling? It's measuring the energy per bit. Yes, yeah. So an FFT spectrum, which gives you units of volts or dB volts, is not the correct scaling for measuring the white noise portion away from the tone. For that, you need to take a look at the amplitude spectrum, where we normalize either per root hertz or volts squared per hertz in order to get to the correct level. So that's FFTs have a lot of capabilities that they bring us, but you also have to be aware of how they're working. Now, one thing that we can do is if we leave, I'll get rid of a couple of these measurements. I will go with the middle one. Now we can back again to my vibration days. If you have a gear train, you have multiple gears turning at different rates. If you have a priori knowledge, top dead center, you can average them together in the time domain. So instead of doing time domain, FFT, and average the FFTs, if you average the time domain signals together, then anything that is synchronous to your start trigger will start to become clearer, because the things that are not related to it will average away to it. In audio engineering, we typically have control of the signal generator. So if I turn on triggering and I turn on synchronous, and as I increase averaging, then that noise floor will fall away. It's going to take it a while, but in a laboratory environment, that's not a bad trade-off. In a production environment, that's just doesn't work, because if it's more than a few seconds. So you can see it's slowly, and I am on the correct amplitude resolution. So this is a trick. If you can trigger, if you have some kind of known thing to give you a reference, then you can use that in order to improve the performance. We use that in production. When we measure our product, we're looking for very low level signals. So then we use the synchronous averaging in order to find the little pins that come out. Again, if there's any questions, happy to take them as we go.
Brian, when there's a comment in the room, could you please repeat it so that we can hear it too?
Sure, but it has been quiet.
Yeah, there was just one, I think. Thank you.
Okay. Okay, so for those that are on Zoom, you can't see my untidy cable mess on the front of the analyzer. But I have 4 signals. I have 2 coaxial BNCs from channel 1 and 2. And then I have 2 channels with speaker wire wrapped up together, just to make it somewhat interesting for a crosstalk measurement. So the first measurement that we'll talk about is a driven. So we feed the signal into one of the conductors. We feed no signal into the other, and we see how much the driven signal is inducing a signal into the other channels. And then we can step through. And you can see that, as we get into, 5.1, even higher channel count systems, this isn't efficient for testing. So there's another technique for testing a crosstalk, which is the undriven. So now we're driving all the other channels except for one that we're measuring. So that's going to be like the worst case scenario. And then inside the analyzer, so actually behind the scene, we're making a series of measurements. And it's going to drive everything except for one, everything except for two, everything except for three. And lo and behold, balanced cables or even coaxial cables are better than speaker wire wrapped around each other. Sometimes the truths are banal, but it is useful. Crosstalk probably is one of those parameters that is slowly falling away, since so much of audio is sent digitally now. But it is still there. It is there in digital. If you have multiple data lines, it's just measured in a slightly different way for it. Some of the other ones that we'll talk about, have a little bit more life to them. Total harmonic distortion, that is one that is plus noise. That is, probably, after level, the next most commonly measured parameter. So here we feed in a signal and we're looking at the harmonics. So let's take a look at how we do that, because this one is an interesting hybrid between the past with band reject filters and the current with FFT analysis. So the blue is the actual signal. The red is a band reject filter. So we're comparing the level of the blue against the sum of the red in order to get that total harmonic distortion plus noise. So let's see if we can make this work. Oh, my apologies. So here is the denominator. We have harmonics. Clearly here and here. So the harmonics over the dominant, that's going to be total harmonic distortion. If we include the off harmonic, here and here, that's going to be the total harmonic distortion plus noise. So that's how they're all, there's three main components in there. There's the actual signal that we're driving. There are integer multiples of the frequency, which is the harmonic portion, and then there's the noise side of things. So total harmonic distortion plus noise tends to be used in the active world because we're somehow responsible for the other frequencies, whereas something like a simple speaker, then total harmonic distortion. And a speaker hopefully is not a nonlinear in the frequency domain, or it's got some other issues in there.
That spot in that diagram where the noise floor dropped away, was that band limiting or something?
Yeah, there's a filter.
Okay.
Yeah, not going out to 50 kilohertz in there.
All right.
Oh, sorry. The question was, what is this notch out here? And that's the low pass filter of that, for the benefit of those who are at home. Yes, sir.
Talk about what would be like are there like application specific tolerance values for PhD plus N? Is okay to be minus 170 in some, while in others are there like more stringent sort of tolerances for PhD plus N?
Yeah, I don't really have a good number to give you. I'll take a look and see if I can you can get some, because in an automotive application, basically it's the background noise. How loud is your expected level relative to the background noise around it. So if you're in a car, sorry, cars tend to have a lot of background noise, so you can handle a lot more distortion in that environment. Whereas if you're in a movie theater or someplace where the background noise isn't masking the pins coming up, then
Sort of analogous to SNR.
oh yeah, we're getting the signal to noise ratio. That's the next one.
Because I always thought of this as like more of a hardware. I don't know, like.
Oh, let me give you a mic so that the people on Zoom can hear you.
Oh, I always thought of like THD plus N to be something like when you're measuring, ADCs, DACs, particularly, and for some reason I always thought it to be like a hardware measurement, hardware in the hardware domain.
Yeah, because you're creating the signal. So how well is your digital signal producing a pure tone?
So the speaker
Counterclockwise.
reference you talked about right now, that's in the sort of associated with the same ADC, DAC components within the speaker.
You're going to have rub and buzz and things like that in the speaker. But yeah, it is more of a D to A to D kind of metric where you're creating the signal. How well is your shaping filter?
Mm-hmm.
One thing that within the speaker world is a lot of times we're using Class D amplifiers. So they're switching power supplies. So they're putting out a lot of high frequency signal. Now, typically the speaker itself is a low pass filter. So you and I don't hear that when we listen to it. But when you're just testing the amplifier itself, then you tend to put in a low pass filter so you don't end up killing your total harmonic distortion by measuring inaudible out of band signals for it. And in the links they'll be sending around, we've got a paper on amplifier testing about some of the challenges that are out there. So remember this minus 107, because when we move to the signal to the noise, we'll be seeing almost the same signal. So the first one we'll talk about is the SYNAD, or the signal to noise and distortion. And it's just the reciprocal. It's 108, 107, but it is the same measurement. It's just the reciprocal of it. It's positive as opposed to negative. And it's measured the same way. You know, we have a band stop filter compared to the level. The next one is signal to noise. And here we're actually making two measurements. So let me see if I can slow things down. So first we measure the signal, and then we measure the noise. Since you work in attendees, you understand how designers could get around that. Have you used the dynamic range AES 17 before? Okay, so if you have a digital signal, you sense that there's no signal on there, you just clamp it down. So then your signal to noise ratio doesn't really represent the dynamic range of the system, because you do have the real signal, but then you have an artificial zero, a digital zero for it. So the Audio Engineering Society in their AES 17, so that first they'll measure the signal. And then they measure 60 dB down. So that being 60 dB down from the initial signal is forcing the digital stream to be exercised and add the noise to it. And then they apply a notch to that for it. Now you may notice the other thing that the AES 17 does is it specifies a weighting filter for it. And that's, you know, one of the challenges that we have generally in audio engineering is there's not a whole lot of standards. And then it becomes, if you're trying to compare two results, you know, from lab to lab, from manufacturer to manufacturer, it's all in the documentation. You know, what's the bandpass that you measured, total harmonic distortion? What's the, you know, what's the bandpass that you measured noise? AES 17 is one of the few standards that we have where it self-documents. If you give dynamic range to AES 17, everybody knows how you measured it because there's a whole standard written around it. Also, it specifies the frequency. There's a link that I'll send out talking about why they use 997 for the frequency as opposed to 1 kilohertz. It's related to exercising all the bits within the A to D converter. So it has a distribution through there. And I'll take that microphone back real quick. This is so the people at home can hear what's coming out of this speaker. Oh, yes. I have my realistic sound level meter. One nice thing about this is you could tell the dynamic range by looking at how much you had. So this one had a massive 16 decibel of dynamic range to it. So there is something nice about working with the older technologies. It was self-evident in there. So like I said, phase is becoming more and more powerful because it's something that we can measure and something that we can control using digital signal processing. So if you've been to a concert recently, the big single speaker is way out of fashion. And now you have the line arrays, and they're using the phase in order to steer the sound through that. In order to make that work, you have to be able to measure the phase naturally and then compensate for it, and also know that it's time invariant with temperature. So all these speakers are being fed the same signal, but there's a slight difference in the phase, which allows it to be steered. Instead of going straight ahead, it's off to the side. Another application is active noise cancellation. So there we have a microphone that's sensing the ambient noise. Through DSP, we're feeding in 180 degrees. We're checking that with an error mic. If we don't really understand the phase that's going on inside those microphones, then that's not going to be a successful technique. So here is my setup for those, well, even for those that aren't looking down on top of it. I have a speaker. I have a 16 MEMS microphone array, 1 through 16, from the side. For this test, I'm not going to be using the reference microphone, but later on, we'll be using that. And as I adjust the angle, should be able to get it to 0. Well, never work with children or live animals. But we'll come back to the phase a little bit later on in the next measurement. So that's probably the, if crosstalk is, ebbing, phase is, something we're still understanding, measuring, and using to our advantage. So the next one that we'll talk about is frequency response. And here I'm going to be just using the speaker into the reference microphone. So the granddaddy of all frequency responses is a tunable filter with a generator. This is a hearing test. You couldn't hear the other part. This is for those who get paid by the hour. But that said, it probably is the most used measurement technique out there. Now, the good thing about using this step sign is that it is just a series of sign measurements. So we have access to things like, THD plus N ratio. I'm not sure I believe that. And THD, because it is just sign measurements. So we can just plot those as a function of frequency. And we've got, we also have SYNAD out here, distortion process. So, it takes it a while, but it does give us a lot of information. So, things we'll talk about, there's measurement time. So in a lab, that's not critical. Production test, number of points resolution. So, you can see that if we, double the number of measurements, we double the amount of measurement time. We got the distortion products, and we also got the noise ratio. So recent one is a log sweep. This became possible around 2000 with some FFT techniques. So this one is going to be a continuous sweep from low to high. Very quick. It gets you thousands of points in the measurement. It might get you almost too many points. It's common with these log type sweeps to actually use smoothing to get rid of some of the high frequency hashes on side of it. Now, because of the mathematics of it, we can't get THD plus N. We can't measure the quiet portion of the signal because we always got signal in it. What we can measure is the harmonics of the fundamental. So we can get total harmonic distortion, but we can't get total harmonic distortion plus N. A subset of that is right now, if you're making an acoustic measurement, you're not only measuring your source and your microphone, but you're also measuring the space, not just the background noise of all the refrigerators, but you're also getting reflections off the wall. I think some of you, at least online, work in room acoustics. You know that you have nodes and anti-nodes within a space. If you're a manufacturer test engineer and you design a box, controlling where the speaker and the microphone are critical because you are measuring a completely different system if you move it around within that. So a technique to get around that limitation and not without an anechoic room, you can always throw money at a problem with an anechoic chamber, but that's not always available. So this is called an acoustic response. It's the same test signal. But what we do is we time weight out after the direct path. So from the speaker to the microphone, that's free field. But by the time it bounces off this wall and comes to that, that's no longer a free field. And that's where we end up with the room entering the equation. So what we do is we apply a filter just before the first reflection comes there. The trade-off we have is that we lose low frequency. So the further away you can get it from a reflection, and that's why we can specify this window either in milliseconds or in distances, because it is deterministic based upon the geometry of your test chamber. So this is a way to get free field response without needing an anechoic space for it. Similar to the other log sweep that we had, we're limited to the total harmonic distortion as opposed to total harmonic distortion plus N. An additional information that we have, especially when you get into speakers, is speakers are inexpensive, but they can have problems to make them ideal. Unfortunately, especially in a headphone, they're right next to your ear, and you hear those imperfections. Distortion isn't the most sensitive parameter for describing that distortion. There are rub and buzz algorithms that go through, and we can perceive that slight imperfection, that distortion would be very small, but somebody would say this is a bad speaker. They don't even have to be trained acoustician. They can just hear it because they've got a pretty good processor between their ears for it. So rub and buzz is a technique to try to match human perception. And that's what I like about audio, because I'm basically a refugee from vibration. You know, the finite element models got good enough that they didn't need to make measurements as much. Audio, because it's human perception of sound, it's going to be here for a good long time. So that is the acoustic response. Again, the log sweep and the acoustic response use the same test signal. It's short, it gets you lots of points, but the drawback is total harmonic distortion. One I didn't mention is it also gets you the impulse response. So a lot of modeling techniques, ISRA, you can take the impulse response, put it into the model. Impulse response is just a different formulation of the Fourier transform in the time domain.
So on this windowing, are there different kinds of windows?
No, it's just simply a time domain to window out the first reflection.
Okay, I thought I had heard of things like Hanning windows or something like
Yeah. That's in the FFT world.
Okay.
And that's where you got to be careful about being, close to the frequency analysis line, where you can have as much as 3 dB error in the level. So this is a time window. That's an FFT window.
Thanks.
Okay. The next signal that we'll look at is a fast sweep. And I stretched it out, but this is essentially a step sweep, but right on top of each other. So if I switch over, now the one thing you can see that you have a pure tone, and then without any discontinuity, it jumps to the next tone and to the next one. So I'll go to a more representative test for that, where I'm testing 31 points. So those are actually discrete tones. For a short period, we can take a look at, the products. So we get back the noise. We get total harmonic distortion plus noise, because, for that brief amount of time, we are just looking at a tone, and then it moves on to the next tone and the next. So we get that additional information of the noise spectrum for it. Now, one challenge that we have with all these different sign-based techniques is that, the DSP is fighting against, the DSP doesn't want to hear the fan in the room, doesn't want to hear the cooling fan on the projector. So it tends to knock down those. So here's another test signal called multitone. And this I liken to the Phantom of the Opera. So this is using 31 tones simultaneously and then pulling off different frequencies. Now, the drawback to this is we don't even get total harmonic distortion. We just get total distortion from this signal. But we do get, strangely enough, the noise density off those 31 tones. So we can characterize the background noise of it. We just can't give you a figure like total harmonic distortion plus noise. And this one does better in going through audio codecs, because it's closer to human voice. So the codecs aren't knocking it down, thinking that it's not something that they should be transmitting. So that leads to the next one, which is
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch. The ship was torn apart on the sharp reef.
So we can simply use the FFT to measure the signal going in, measure the signal going out, and get the transfer function between them. So now your codec is quite happy, and it might go a little bit mad listening to the same phrase over and over again, but then you can get a frequency response from that system. So the first test that I ran here, the low frequency for a transfer function doesn't seem quite intuitive, that the MEMS speaker, I would expect it to climb, to be flat. I don't quite understand the low frequency. If you take a look at coherence, coherence is a measure between the response to the input. Low coherence means that what you're getting out isn't coming from what you're putting into it. Unity, value of 1, means that what you're getting out is what you put in. Low coherence means the energy is coming from somewhere else. So in this situation, I am measuring the MEMS microphones back to the generator signal. So any losses that I have in terms of the speaker or in the microphone, that's where my low coherence is. The next setup is I have that reference microphone against the 16 MEMS, and now I'm going to reference the MEMS microphone against that reference microphone. So now all this lovely HVAC noise in the background, both the microphones are seeing it. I actually can use that energy as part of my measurement. So I'll jump to that one.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch. The ship was torn apart.
Right. And here you can see the phase isn't perfect. I still have some other frequencies that are putting energy in, but it's much better. I also get the phase, and since the first microphone receives a signal much sooner than the last, then it'll fall away from there. So a transfer function is a nice, something that the technology allows us to use. Okay, so just to kind of go through and make sure, because it's always good to revisit. We talked about units, dBV, dBu, decibel in general. You have one more corny joke that you can use in the future. Talked about crosstalk, the different ways of total harmonic distortion plus noise, simple total harmonic distortion, and then the special case, the multi-tone total distortion. Talked about all the different ways that we can measure dynamic range. We can either measure it on the meter itself, we can put in a notch filter, or we can do a more elaborate technique where we feed in signals at different levels in order to exercise a D to A or A to D converter. Talked a little bit about phase and its importance, and then went through a 1,000,001 ways to measure frequency response. Again, we'll provide kind of, if you're interested in any of these, we'll send links to various documents, videos. Again, 40 years of AP, they have produced a lot of materials for it. I do appreciate Dan. Thank you for setting this up, and Rod, my boss somewhere. Dan, thanks for letting me work on this. And thank you for your coming in and sharing your time.
Are you still taking questions?
Oh yeah, I'm open.
Great.
At some point, we'll have a tour here for those that are physically present. We're going to try to do a little bit remote as well. But yeah, certainly open the floor to questions.
I had a question about the sentences that they're using to do that testing. Are those words containing
Yes,
frequencies or
yeah, those are
ampli-
special, that exercise, all the different frequencies.
yeah,
And they're available online, those recordings.
I keep thinking that those are intended, you mentioned codecs, which implies cell phones and such, and that you're trying to transmit an intelligent signal over a bandwidth that in analog world would probably not handle it. And so is that what you're intending?
But also noise cancellation.
Okay.
There's a lot of, and then maybe I'm using codec incorrectly. I'll lump it under digital signal processing, techniques. So it's not just lossy compression, it's also getting rid of echoes. And
I'm remembering using a technique in recording where I used a pair of microphones at slightly different distance from the instrumentalist, and suddenly the room coloration drops away. I'm sort of wondering if that was perhaps part of the intent of the MEMS microphone, because you have
MEMS are kind of very much used for beamforming.
okay.
So when you're working on your phone, the phone wants to listen to you coming from direct and wants to ignore the sounds from behind. So then they'll use the phase to focus on you and get a cardioid or even better sensitivity to the front and less to the back.
I'm aware of some of these microphones for conference rooms where they are an array, and they phase align to whomever is talking somehow automatically. So
Yeah, and because the price per microphone channel has just fallen away with MEMS microphones, then there's a whole world of applications. But we had other questions. If you'd be the. I
think there were some in chat as well.
Oh, okay. Dan, were there some questions in chat that you see?
no, there aren't. But I had a question about the phase that you briefly showed of the line array, it looked like, and you showed the phase changes from one element to another. It's back a bit. You had a line of speakers.
Oh, this one.
Yes, that one. And now the next one, one more, I guess. You showed some there was a bar graph of horizontal phase changes, I interpreted.
Oh, okay. Yeah, in the measurement that I didn't get to work quite
Yes. Yes.
so well.
My question was, that one didn't work so well, you said, but should it have been, the bars were not, they got bigger as they went down the screen, so longer. And should they have been equal increments from one to the next? They're kind of jagged.
Yeah. Now some of the jagged would be mic to mic variation. The general line would be the physical positioning. So let me see if I can get that one.
Because beam steering is a fascinating subject that used to be completely impossible, and now is something that a variety of. Yeah, so it's long and then shorter and then long and then shorter.
So I think
and
if
long.
I get it. There we go.
yeah, okay, I got it.
So now anything that's not along the smooth line, that's going to be variation from one mic to the next microphone. But there should be a fairly straight line between there.
If you drew a line from the longest one at the bottom to the shortest one at top, should that be a smooth line?
Yes.
Okay.
If the microphones were perfect, then that would be a smooth line because
And
the
the
geometry.
generator was perfect. The sources were
The source
perfect.
isn't bad at this frequency. You know, at the higher in frequency you get, the more directivity that you'll end up with. So
Right. Until you make a very long line.
yeah.
Auto scaling was making it worse than it was.
Can you
Yeah.
hand him the mic, please?
Oh, sorry. Sorry. Apologies.
Part of it was the auto scaling. So when the capsules were all perpendicular to the loudspeaker, receiving the wave at about the same time, it looked worse than it was because you could see it was zooming in to about plus or minus 4 degrees, whereas when they're in line and there's a delay between them, the range was much larger.
Yeah. And this is just a test board we make because, you know, you can't ask Apple to pull off the digital lines on their circuit board. So in order for us to do our demonstrations, we created our own simple board.
Okay, cool. Thanks. Other questions?
Okay, then if we're up for it, then we'll try to take a short tour
Great.
facility. And those of you on Zoom, we've got a rolling trolley
Yes.
that we'll try to bring you along.
So you
one
need
thing-
to stop your sharing.
Yep. And then if you'll let me, I'll try to get back into the meeting on my phone
Yes.
so we can have portable.
Yes, and I will spotlight Rod.
There is a chat question right now.
Oh, go ahead, Gary.
In the chat from Dave Quick, the question is, I noticed that the spoken word text were male voices. What would be the effect of using female voices?
Different frequency content, also different languages have different frequency content as well. So I think, you know, a lot of the telecom people are used to having, you know, different, you know, genders and accents for the testing.
So we'll need to mute your computer and only have your phone, the microphone of your computer, but leave the speaker on, I guess. I'm not sure of that. So your phone is muted now still.
Okay, now we're on the phone, and then we've got a phone as a speaker. All right,
Yes.
you gonna follow along, Rod? Are you gonna lead, Dan, or should I?
You lead, please.
No, other Dan.
Oh,
Sorry,
other Dan, sorry. And Rod, your microphone is not on now.
Not on. I have the handheld.
The handheld is not on now.
Should the handheld be held
No, we're going with this one.
Yeah, we're going with the phone.
so I can leave this here?
Yes.
Okay.
Okay, we're gonna file through a room. It's gonna get a little narrow. So we're just gonna go in a straight line. Okay. And I'm gonna go to far end and turn on the light.
There could be some background.
Nope, I'm gonna do it from the other door. I'll meet you in a second. Okay, so one at a time, but just form a straight line. So what we have going on in this room is what we have in these two racks that you're passing is This is one of every analyzer we currently make connected to some kind of a controlled device under test, which in many cases is an unexciting cable. But what happens is every time we change something in the software, we spin a build of the software and it gets installed and run on all of these things through a few thousand automated tests. So that's going on continuously. It's actually going on right now. That's how we do our regression testing on the software. On this side, these are instruments that are set up for less systematic tests, generally when we need to do some type of special use test. Maybe somebody in this room reports a bug. So that's less exciting. That's just IP crap. And then in the closet's the water heater. But I'll encourage you to just flow through that door. You can show the participants the racks if you want. Any bugs to report, Tracy? All right. Oh, I forgot to point out the safe where we have our lifetime supply of AKM converters that we bought just before the fire. All right. Depending on your perspective, this is where the real magic happens. We'll just start at the back end here. I'm sure you have all seen a shipping and receiving area before, but what we do here a little bit differently than some companies is we're on a full, you may have heard the term lean, or if we're being honest, Toyota production system. So what happens is when an order comes in, it actually starts at the back of the system. So we pull orders. So what we'll do if we come around right here, and actually, hey, Brian, can you find the lights and turn them on? Thank you very much. So if everybody just follows me around. So really orders actually start back here, which is where our shipper lives. And our shipper pulls the order. And if we come thread our way this way, we'll just wander all the way through the production process. Don't be shy. Just don't touch anything. Mostly for ESD concerns. We'll also take credit cards. But actually what we have out here is the output of our calibration lab. So in this little room, and we'll get a chance to look at that as well, that's actually sort of a separate entity. That room is the Audio Precision Calibration Lab. It's an accredited facility. Every instrument we ship comes with an accredited certificate of calibration. When you order an instrument, either it's something that we have ready to ship, it's on hand, it's been calibrated, everything's good, and we'll just pull it off the shelf and ship it, or we'll pull it through the calibration lab and it will come out here. We keep following that back, and luckily we are shut down for the night, so we can all do this. So again, we'll just have to thread our way through this space, but in the typical fashion. And our calibration guy will probably report a nasty temperature anomaly tomorrow. He did his job. Yeah. But what goes on here is instruments actually come in from this side, and we have this handy thing. So these are all instruments that are waiting to be calibrated. Calibrator pulls it off. We've got 3 stations where we can calibrate the instruments. And exactly for us, the key is we have to keep this room plus or minus 1 degree centigrade. Calibration takes between 20 and 45 minutes, and then it goes to where you just saw. And then if we wind our way back out, again, we're just going upstream. So here is where we set the voltage of every instrument, depending on where it's getting shipped, and QC test happens here. So if you're going in the other direction, it goes QC, calibration, shipment. And then what you have here is a fantastic pile of money. So these are all chassis that are built and waiting for somebody to tell us how they would like it configured and what options they need. So this is everything from APX 555s on down. You know, to give you an idea, these little things are about 50 grand all the way down to about 6 grand. And the empty spots, so the way it actually works is each one of these spots should have a chassis sitting on it. The person actually who works right here, he comes in every morning, he sees what spots are empty, and he starts building them. And around the corner here, each one of these boxes is filled with the components that make up an APX. So order comes in, that person pulls it from there. If there's not something to pull from there, it gets pulled from here. If there's not something to get pulled from here, it gets built here. And then again, going further upstream, this is where sort of something visible would happen. So all along this row is, if you will, where the real magic happens. So this is where the technicians who build and adjust all the analyzers work. So they come in, they have circuit boards, they bring those circuit boards up, they adjust them, then those get turned into chassis, chassis get QC'd, calibrated, and out the door. And if you really want to see cubicles, I will show you cubicles, but that's all that's going on in the rest of the building. Sorry? I've lived in a lot of cubicles in my life, and I cannot say that ours are special. All right. Any questions? Okay. Do we eat the leftover donuts, or how does this work now? Okay, let's go this way. We'll look at a few cubicles. Conference rooms, beautiful conference rooms. So one thing I'll show you, I guess, is this is what we call the production board. So this is actually literally, not metaphorically, a digital analog of what you just saw there. So each group of cells here represents an actual order. And at the top here, where it actually is in the production process. And the purpose of this is we're part of Axiometrix Solutions. The sun never sets on Axiometrix Solutions. Most people are not here. Most employees are not actually here physically. So they can log onto this and see what's going on with any particular order in real time. All right. I'll walk you back. Here is we call this the museum. It's sort of more like a collection of stuff we haven't thrown out. Some of our old stuff, some of our competitors' old stuff. I can't, someday we plan to organize it.
See a few tech scopes in there.
Yes. So the history of audio precision is that the four founders all came from Tektronix. They all worked on this product, which is the 500 series modular frame from Tektronix, and specifically it had an option called the AM500 that was a audio analyzer for that modular frame. I think the story I'm allowed to tell now that the statute of limitations has expired is the 500 series was replaced by the 5000 series. There was supposed to be an AM5000. There wasn't an AM5000. The founders all quit over that decision and started Audio Precision. And a couple years later, the System 1 shipped. 40 years ago, the System 1 shipped. Yeah. That is a virtue, and we're proud of it. We maybe also wish it wasn't so. Well, we did make tens of thousands of them. Very well. All right, and then actually we'll just be going around the corner and back where we started.
All right, did you guys all get a chance to eat something?
We are snacking now.
Excellent. I see that lovely spread of food.
You see Brian? Oh, there he is. Thank you very much.
Thank you. I'd just like to make it known that I drove 150 miles to get to this meeting, and the BIAMP guys only had to drive 2 blocks. I don't think it's fair.
It's funny how that works, isn't it? Okay, I'm removing the spotlight from Rod. Thank you for that, Rod. That was really a great tour. And it was wonderful to be online and be able to see it. So thanks, everybody. I think we will separate now so that the people in the room can visit and chat. And is there a time limit, Brian or Dan?
No, I mean, maybe another half hour. We do have goodie bags for those that did make the big drive or walk, in the case may be.
Great.
And we will be sending around those links to different documents if anybody wants to get into deeper details.
When will you send that, and how will you send it?
I'll send it to you, Dan, if
Okay.
that's all right. And
Is it
then-
possible to do it while people are still in this room? Because we won't be in this grouping again ever.
Oh.
I could put it in the chat, or you could put it in the chat.
Sure. I mean, it's an Excel document. Is that going to work?
Good.
Yes, I'm seeing yes.
Okay.
Yeah, put it in the chat, please. And then the people who are here will grab it. And for people online, we'll continue talking after this, and people in the room can continue talking in small groups or whatever. Online, we can only do one at a time, but in the room, you can have as many side conversations as you want.
Although Bob Ward did have a question in the chat.
Yes, that's true. Bob said, can you tell us a little about the gear used for calibration? Is it linked to NIST?
Oh yeah, we're A2LA accredited. So everything is traceable back to the National Institutes of Standards. Accreditation and calibration means that we have an external organization come in and review our uncertainties in our processes.
Great.
Do you see the link?
Not yet.
Oh,
You need to
sent.
put it in chat and then send it.
Oh, I didn't hit
There it
send.
is. Yep.
Yep.
We got it. Thank you, Brian, for a wonderful presentation and tour. That was terrific.
Yeah, it's always nice to share with different parts of audio because it is a big elephant.
Yes, yes. And thank you for supporting the AES and the section. And I'm looking forward to working together and publicizing our meetings in Oregon. And it's probably premature to talk about how we're going to address that, maybe, but we'll put that in our news
We'll have maybe have a post session to go through.
Yeah, exactly.
In the next couple of days, maybe not before the end of the month, since that's what part of the reason we have so much stock is the end of the month buildup.
Ah, okay, great.
I had one last question. One last question. You mentioned, sorry, I've got my mouth full. Early in the conversation, you mentioned the 600 ohm load. I keep thinking, is that not from the telegraph era with a pair of lines strung over a long distance? And was that the so-called terminal impedance for that kind of a transmission line?
I'm not sure, but it definitely in the audio measurement handbook, I think it goes back to where that 600 ohm came from. Also, I think 150 ohm was also used at times.
Yeah, I mean, one of the, of course, twin lead is nominally, shielded twin lead is nominally maybe 120 ohms or something like that in that neighborhood. But then I'm also dealing with a ribbon microphone preamp that is, when you look at the interior of it, there's a triad transformer. You go back to the old catalogs and it says 100 ohms to grid, which you plug your ribbon microphone into that. You cannot plug a condenser microphone into that kind of an impedance without overloading it. So as I say, you know, how much of this all relates to the old telephone company and their
they were
the wires that hung out on the telephone poles. But, okay.
But we'll probably sign off from here, from Beaverton, and
okay, and we'll keep going online. Thank you again so much. Take care.